This is the third and last part of chapter 11. We're going to talk about the rest of the reactions that we didn't cover in part 2. The first one that we're going to do is a reaction of alcohols with phosphorus halides. Now this reaction is actually very useful. It goes in very high yield, so you don't have to worry about rearrangements or anything. You take your alcohol and you add your phosphorus trihalide. This one is phosphorus tribromide. And the reaction will substitute the OH for the bromide. It's a nice little substitution. It works for primaries, secondaries. It works for tertiaries too. But we focus on primaries and secondaries because those are the ones that don't react well with HBr or HCl. If you have a tertiary alcohol, then by all means just throw in some HCl or HBr or HCl. Well, I said that already. But the reaction will actually go without problem. If you want a chloride, you could use phosphorus trichloride. I prefer the PBr3 for the bromide, and then I'm going to show you thionyl chloride for chlorides. But again, it gives you good yields with primaries and secondaries. The mechanism itself is, again, we're going to see the OH being turned into a good leaving group. So you have your alcohol, the oxygen of your alcohol attacks the phosphorus and it displaces one of the 3 halides. And now that you have your oxygen attached to your phosphorus, this right here is an excellent leaving group. What does a leaving group does best? Then it leaves. So the halide that we displace, the disgruntled halide, will do an attack on the carbon, and that will displace your whole leaving group. This is a whole leaving group. And that's how you get your OH substituted for your halide. This can actually go into the reaction. It still has 2 halides, so it can react 2 more times. So you're not wasting PBr3. It can give the 3 bromides that it has attached to it. If you wanted the reaction to do a chloride, I prefer to use thionyl chloride. And the structure of thionyl chloride, it resembles the one of DMSO, but instead of 2 methyls, you have 2 chlorides in there. But again, you can take a primary alcohol, and now I have a little insect flying all over the place. Thionyl chloride will substitute the OH for the chloride. If you have a secondary, the reaction will still go very nicely. The byproducts of this reaction are SO2 and HCl. They will both bubble out of solution, so you actually just get your product in there. And the rest of the products just go away. I don't usually write them, but I know that some of you prefer to see them. This will be the last time I'll actually write them out. Alright, now let's talk about the stereochemistry of these 2 reactions, because the reaction itself, if you go back to the mechanism of the PBr3, the reaction that we're looking for is an SN2. And if it's an SN2, you and I know that it goes with inversion of configuration. So if you happen to have an optically active alcohol, then you have to watch out. So I'm going to put this alcohol right here. Is this R or S? Let's do it. Okay, so this is my chiral center. Oxygen is 1. Carbon is more important than just 1 carbon. So this one is S. When I do the reaction with either PBr3 or thionyl chloride, both of them will do an SN2. But it's that inversion of configuration that we're going to have. So our product the bromide will attack from the back, and if it attacks from the back, it stays in the back. And this one is now 1, 2, 3, but there's a hydrogen in front. So it's S, but the hydrogen is in the front, so it's the opposite. It's R. So you see I have that inversion of configuration there. Let's do oh, I keep putting them in the front and I don't know why. I'm sorry. I'm going to do thionyl chloride so that you see them both doing the inversion of configuration. Again, I put the OH in the front, but we're going to have inversion of configuration so that chloride is going to be in the back. And now I feel guilty, so I'm going to go ahead and put it in the back in one of them. I'm going to do PBr3. And now I have my bromide in the front. By golly, we're going to have it all. Can you see that? I think you can. Okay. Alright, so remember that when you use either PBr3, phosphorus tribromide, or thionyl chloride, your reaction will be an SN2. So you have to obey all the little rules about the SN2 reaction. And the first one is that it's an inversion of configuration, and that it would be easier to attack a primary carbon than a secondary carbon. Now I'm going to show you a reaction that it resembles ozonolysis, but it's with a diol, and it's a glycol, which is another name for a diol. So what we're going to do here is that we're going to actually just take a vicinal diol. It has to be vicinal. And we're going to actually break the carbon-carbon bond between them. And then we're going to oxidize. So again, it has to be vicinal for this reaction to occur. If it's not vicinal, you're not going to have this reaction. And you add periodic acid, HiO4. Again, the reaction, it's like an ozonolysis. So you're going to break, you're going to cleave the bond, you're going to separate them. Notice that I put a nice and symmetric alcohol. And you're going to oxidize once, both sides. So this one, there's a hydrogen there, so it's still going to be there at the end. And this one, it's still going to be an aldehyde. So this one, because there were hydrogens right here, you break the bond, but you don't do anything else aside from oxidizing to an oxygen. So that hydrogen stays there. I'm going to do, let's do one that, okay, let's do this one. Okay, so now that one, when you break here, you add periodic acid. You break the sides and you oxidize them once. One side had a hydrogen, so it gives you the aldehyde. The other was a tertiary alcohol, so we broke that one, but there were still two carbons, so it's a ketone. Let's go back in time and let's get a couple of reactions that can get us that diol. Let's do a review. I like reviewing. Reviewing is good. All right, so here's what we're gonna do. What are we gonna do? Okay. Let's start with the double bond. I mean, I could start with an alkyl halide and then make the double bond, but I want you to remember that if you actually make an epoxide first, and then you open it with water. What type of diol would we get? We get the syn or the anti-diol? I'm gonna let you think it up, think it up. You get the trans diol. How do you make the syn diol? Do you remember that one? Okay, I'm gonna make the syn diol. I'm gonna use osmium tetroxide. So osmium tetroxide, and then so that the osmium leaves behind the 2 oxygens, I give it more oxygens, and that's why we're adding hydrogen peroxide. This one gets you the 2 OHs on the same side, the syn diol. But it doesn't matter. If you add periodic acid doesn't really care whether they're syn or anti. What it cares about is that they are vicinal, that they're next to each other. So we're going to actually break the bond between them. I can't breathe. And we're going to oxidize once. Don't break anything else. Well, I'm gonna make a super duper long bond. And now I don't like this the way it is, so I'm going to open it up a little bit. 1, 2, 3, 4, 5, 6, 7, 4, 6, 7. Ketone. 2, 3, 4, 5, 6, and aldehyde over here. So this is the product once you kind of straighten that chain out. We learned this reaction a long time ago, well, 2 chapters or 3 chapters ago, and now I have an extra step from a reaction from this chapter. All your reactions go together, so make maps of the reactions that you have. Oh dear. Oh, this is well, it's a good reaction that it's not such a good reaction. But let me just show it to you. It's a Fischer esterification. And then esterification, it's when you form an ester. The ester, it's a carboxylic acid that instead of a hydrogen on this side, it has a carbon group. It can be the same as you have on the left, or it can be a completely different carbon group. But I'm going to do the box reaction. So the Fischer esterification starts with a carboxylic acid, and then you add whatever alcohol you want. I'm going to just do it in a different color because I need you to see what oxygen ends up attached to where. And a long time ago, they used to teach reactions by showing you what you were losing. So we're losing water, we're condensing 2 molecules, and we're losing a water molecule. That has absolutely nothing to do with the mechanism, but it shows you that you're going to put those 2 molecules together. For this reaction, I am going to need a little bit of acid, just a catalytic amount of sulfuric acid, and the product, it's going to have the carbonyl with all the carbons on the left, and this oxygen is the one now attached to the carbonyl. So this is the Fischer esterification reaction. Now here's the problem with the Fischer esterification reaction. It's an equilibrium. And if you have an equilibrium, that means that the reaction can go forward, forming your product, or it can go backwards, forming your starting materials. So it's not a reaction that will give you 100% of your product. So it's not considered to be a good reaction. Now here's what we're going to do. We're going to change this slide. We're going to cover this one first, the reaction of alcohols with acyl chlorides. Because this reaction, if you want to make an ester, this would be the reaction to actually do. So I'm going to use the same I made a mistake. Instead of the OH, put a chloride right here. I don't have my magic erasers. I don't think I have any magic erasers here. I'm in my office at home and my erasers are in my office at work. Alright, I'm so sorry. Put a chloride there, please. And then just put an alcohol on this side. So it doesn't, the difference between the Fischer esterification and the reaction of alcohols with acyl chlorides is that instead of a carboxylic acid, I have an acyl chloride, which is just a chloride instead of the OH. All right, we're going to be eliminating HCl. So we're going to use a box reaction right here. The mechanisms of this reaction, you're going to learn them in the second semester. So it's not like I'm giving you a free card. Oh, they're coming. All right, so this reaction is not an equilibrium. Once this reaction is done, it's done. And it will actually get together and form the exact same ester that we were hoping to make with the Fischer esterification, but this one actually makes it in high yield. So this one is a much better reaction. All right, now we can do the problem. Because the problem, I'm going to allow you to make this, but I am going to limit you to the one that gives you the highest possible yield. But I'm still going to do a review of everything. So here's your review. There are two ways of making this. The first way would be to actually just do the Fischer esterification. So you have the carboxylic acid and the Fischer esterification, and you add the alcohol. So this alcohol right here. Again, the reaction suffers from an equilibrium problem that the reaction can go back and forth. And you don't want a reaction to go back and forth. You want a reaction to go forward and produce what you want, because that's the whole point. Would you please go? I don't want to kill you. Go. So I'm going to put here not 100%. Well, you're insistent. Again, this is the Fischer esterification, not your best reaction to make esters. But if instead of a carboxylic acid, we use an acyl chloride, this reaction is going to be much better. It's not an equilibrium reaction. It gives you a really nice high yield of your alcohol. So this is the much better way of actually making this ester right there. Oh boy. Okay. We're going to form an ether. And the ether, it's an oxygen that has two carbon groups, one on each side. The carbon groups can be the same, which would make a symmetric ether, or they can be different, which would make an asymmetric ether. But When you're talking about the Williamson ether synthesis, you're talking about, I'm going to use an alkoxide that you know already. I'm going to use the terbutoxide. And I'm going to use it because we said that that was a bulky base that likes to do the E2 elimination. Well, sometimes it does SN2. And that's the whole point of the Williamson ether synthesis, is that the Williamson ether synthesis is banking on an SN2 reaction. So I have my terbutoxide, my bulky base. And what happens if I add methyl bromide to it? Can I make a double bond with methyl bromide? No. No, you cannot. Because you only have one carbon and you need at least 2 carbons for a double bond. So the oxygen will attack the carbon and will displace the halide, and it will make an ether. This is the Williamson ether synthesis. You take an alkoxide and you do an SN2 reaction with the alkoxide. So it's an alkoxide, not this one, not just this one, and an alkyl halide. That makes the Williamson ether synthesis. And you have to remember that it's an SN2 reaction, so a methyl halide is going to be better than a primary. Primaries unhindered, much better than primaries that have other groups close by, hindered primaries. Way better than a secondary. Alright, so you have to remember this, the SN2, the alkoxide, and the alkyl halide, because now I'm going to show you a problem. This is the last slide. Oh, well, that's a beautiful problem. I'll make up a problem as I go. Let's do, okay, here it is. I want you to actually prepare this ether right there through the Williamson ether synthesis, and I want the highest yield possible of ether. And then you start thinking, okay, here's how you do it. You have 2 possibilities. You know it has to be an alkoxide. So it's a negative oxygen and an alkyl halide. That's your Williamson ether synthesis. So here's what you're going to do. Your alkoxide can be either the left side, this is the alkoxide, the other side would be the alkyl halide, or this would be your alkoxide and the other side would be your alkyl halide. Those are your 2 possibilities. So let's work on this possibility first. I'm going to have 2 possibilities. I get this alkoxide right here, and I'm going to take the other side, the 2 carbons, and I'm going to add a halide of my choice. The halide doesn't matter. I'm going to put a bromide. What matters is that this alkyl halide is primary. That's what really matters. All right, what is my other choice? My other choice is that this is my alkoxide. And the other side, I'm going to make it into an alkyl halide. Ah, this is moving. No! Dang it. I knew that drinking the NyQuil before I started this was bad. Okay, bromide, here. Bromide. Erase the negative charge. This alkyl halide, because that's a bromide, again, that's nothing, that's a bromide. This is a secondary alkyl halide. All right, you need to do the best SN2 possible. The question is, what's better for an SN2? A primary or a secondary? What's your answer? Did you answer the primary? because that's the right answer. Okay, this is a much better SN2 reaction. So this is the way that we're going to actually make the ether. But we're not done. No. Now you have to actually make this. And we're going to use reactions that we know, that we have learned before. Okay, so we're going to take the alcohol. And in chapter 10, we learned that if you add sodium hydride to the alcohol, you deprotonate the alcohol. I like to put my charges. You don't have to. Now we're going to add that primary alkyl halide right here. And that's the Williamson ether synthesis. This step right here is the Williamson ether synthesis, because this oxygen is going to attack the carbon that has the halide and displace the halide. And that's how you get the highest yield of your ether. You have to watch everything that has to do with the SN2. You have to make it the best possible. So I have a really strong nucleophile, and I have the smallest alkyl halide possible. All right, I apologize for the mistakes. I'm still sick, but I feel much better today. So I will see you this week. Bye.